Okay, so welcome once again to Harcourt University. Now, today we are going to solve some problems under vibrations. I mean, a quick revision for your mid-semester exams I know coming up very soon. This goes to students of K University at the moment. I mean, if you are anywhere in the world, this is just some questions that we are going to take to revise some concept under basic vibration concepts. Now let's get into it. Now in these questions, we are going to solve questions under free damped systems, free and damped systems, whirling, resonance, force systems, and rotation of unbalanced masses, and maybe some concept of transmissibility. Now before I get into it, together with my students, we came up with some formula sheets, the equations involved in the vibration course are a lot and can be written in so many ways or some different forms. So we came together to put some formulas together as a formula sheet, and we have them here, right? So before we begin, if you want this, I mean, they are PDF sheets. So if you want them, if you are interested, let me know in the comment section. Maybe you can send your email and I'll send it to you directly. All right, so let's get into it. Now, the first question, we have a preamble. So a model of Toyota front suspension is shown in figure 1A and a simplified model shown in figure 1B. And we are using this information to answer question 1 to 8. Okay, so we have initial conditions, displacement. Initial displacement is 1 millimeter. Initial velocity is negative 2 millimeter per second. All right. So here we have a mass of 100 kilogram. We have two springs in series together with another one, which will be a parallel, arrangements, and we have two dampers in parallel. And we have to model this to look like this. So we need to find the equivalent spring constant, equivalent damping coefficient. All right, so before we begin solving the questions, kindly subscribe to the channel if you haven't. All right, and if the video is okay for you or if you're learning anything, let me know in the comment section. All right, we need to reach 1,000 subscribers and 4,000 watch hours to get to the playlist, and we can't do that without your support. All right, so if you are here, kindly hit on the subscription button to support what we do here. Now let's get into it. So question 1 asks us to find the equivalent stiffness. All right, so we are going to find question 1, we are going to find total K. Now with the total K, realize that we have this and this are in series together, are in parallel with this. And when springs are in series, you have K to be equal to 1 over K equivalent will be equal to 1 over K1 plus 1 over K2 up to how many Ks we have. All right, so that means the total K when they are in series will be equal to 1 over K1 plus 1 over K whatever. Then you take the inverse. All right, so you reciprocate it. So for the K values, we are going to have question 1, we have 1 over 2,000 plus 1 over 3,000 all inverse plus, and when they are in parallel, it is 1 plus, you just add them, right? So if you take the inverse, I'm going to get the equivalent, then you add the 1,000 kilonewton per meter, and this will give us 2,200 newton per meter, which is same as 2.2 kilonewton per meter, and the answer is B. Okay, question 2, you are supposed to find the equivalent damping coefficient. Now dampers and springs are resolved just the same way. So here we have this damper and this damper in series, in parallel. So we're going to have C total to be equal to C1 plus C2, and that will be 500 plus 100, and that is 600 kilogram per second. Question 3, we are supposed to find the damping ratio of the system, and damping ratio is equal to C. Okay, so we have C over CC, all right? And so we can say that we need to find CC here. Okay, so CC, which is the critical damping coefficient, is 2mk. Okay, now let's go to our formula sheet previous. Okay, so when we come to free damp system, this is the equation, right, for the damping ratio. All right, now the C can be written in terms of, so we can have C in terms of mk. Yes, supposed to be C in terms of mk or omega n. All right, so C will be equal to 2 root mk or 2 omega n m. All right, so anyone you want, if I choose this, I have to first find omega n, so I rather will go for this. So CC will be equal to 2 root 100 times the equivalent K, 2200. Okay, and that gives us 2 root 100 times 2200. So CC, we have 938.083. All right, and the C is 600. So we have 600 out of 938.083, and that will be 600 on 938.083. We have 0.6396. All right, so 0.639, you have 0.64. This is correct. Okay, this one is also correct. All right, so let's move on. So question 4, determine the natural frequency. And from our formula sheet, what's natural frequency? We have root k on m. All right, so determine the natural frequency. Omega n is equal to root, so we are on question 4, root k on m, and that will be equal to square root of 2200 out of 100, and we have roots of 22, and that is 4.690. So this is true. And then let's determine the damp natural frequency. So let's go to our formula sheet. Damp natural frequency. So this is the response. So when it comes to damp natural frequency side, we have omega d to be equal to what? Omega n root 1 minus zeta squared. So omega d will be equal to omega n root what? 1 minus zeta squared. So we have 4.690 root 1 minus what? 0.64 squared, right? And that will be 4.690 square root of 1 minus 0.64 squared, and we have 3.6. Okay, so we have 3.60. This is also true. Determine the period of oscillation of the system. Now, for damped systems, you use omega d when you are finding the period. So our period t will be equal to 2 pi over omega d, and that will be 2 pi out of 3.6, right? 3.6, and that will be, so 2 pi out of 3.6, we have 1.745. So 1.745, the same as 1.75. So here this wasn't true. So yes, we have the period and amplitude of oscillation in millimeters. So let's go to our formula sheet. The amplitude for free damped system, we have what? X naught root X naught omega d all squared plus X dot naught plus omega n zeta X naught all squared all on what? Omega d. Okay, so our amplitude from the formula sheet, we have square root of what? X naught omega d all square plus X naught dot plus omega n zeta X naught all over omega d. Okay, so X naught is the initial displacement, X dot naught is the initial velocity. When we come to the problem, we had what? Initial displacement to be 1 mm, initial displacement to be -2, initial velocity to be -2. So our amplitude will be equal to square root of X naught 1 omega d 3.6 all squared, then plus -2 plus omega n was 4.69, and then zeta 0.64 X naught 1 all squared here all over omega d 3.6. So A will be equal to 3.6 we have 1.037. All right, now let's see our answers. We have 1.00, so we don't have exactly 1.037. You might go for this, but since it's 2 dp and it was left in 00, I don't think that's advisable. So you can go for this, but you can write your answer 1.037, and then maybe you choose none of the above. Now the next is the phase angle. So phase angle, let's go and check. Phase angle is here. All right, and then we have what? Omega d X naught all over X naught dot plus omega n zeta X naught. It looks smaller here. If you have the sheet yourself, you can view properly. So let me know in the comment section if you want the formula sheet. I'll send it to you for quick revision before your exams. So the phase angle phi is equal to tan inverse of what? X naught omega d all over X dot naught plus omega n zeta X naught. So phi will be equal to tan inverse of, here X naught is 1, omega d 3.6, -2 plus 4.69 and 0.64 and 1. Okay, so our phi will be, so set our, so you can find it in terms of, I think the answers are in radians, right? So you need to set your calculator to rand mode. Okay, so, or you can find it in degrees and multiply by pi on 180, and that's also fine. So tan inverse of 3.6 out of -2 plus 4.69 multiplying 0.64 multiplying 1. Okay, so in degrees we have 74.45. Then you multiply by pi on 180, and that will be 74.45 times pi on 180, and I have 1.299, approximately 1.3 radians. And what do we have? We have 2.1, 1.0, so none of the above. 1.3 rads here. Okay, so that is that for the first problem. And now the first problem we're supposed to do up to question 8 from the preamble, question 1 to 8. Now the next we have rotates a fan is mounted on a spring and a viscous damper impulse so that the linear motion in the vertical direction occurs. Okay, so we have a problem of rotation of unbalanced masses. So let's see how we go about that. Okay, so I've used up my space. I want to clean apart. Yeah. Okay, so here we are given that the mass here is 40 kilogram and the rotating unbalance is 10 kilogram millimeter. So ME is equal to 10 kilogram mm. Take the damping ratio of the system to be 0.4, so zeta will be 0.4, and the fan speed omega to be 1500 rev per minute, and we have to work with what's rad per second, so you multiply by 2 pi on 60. Don't forget that. So I want to do this before I forget. That will be 1500 times 2 pi on 60, and that's 157.08. 157.08 rad per second. And what else do we have? We have transmissibility, so TR, which is equal to square root of, we don't have to, let's go and check our formula sheet. So we have transmissibility here. This is it. F naught over F, FC over F naught is equal to what? Root 1 plus 2 zeta. Let me increase this a bit. Okay, so you can see we have what? FC on F naught to be square root of 1 plus 2 zeta tau all squared and everything here. So yes, once again, if you need the formula sheet, let me know in the comment section. I'll send it to you. Quick. Let's move on. So, oh yes, before you move on, please, if you've not subscribed, kindly do that. All right. You are doing this, supporting me, supporting yourself, and supporting the next generation. But if I can keep doing these videos, the next generation wouldn't have to suffer in class. All right. So thank you for your support. Let's continue. So from here, I don't want to write the formula yet. So let's just write the value given. So TR is given us what? 50%. All right, so it's ratio, so you can put it percentage, and this is the same as 0.5. What else do we have? What is the amplitude of vibrating of the fan? So let's go and check the amplitude of the vibration force, right? So we come to the equation. The vibration force is the component here, right? Is the component here. Let me open it up. So this is the free vibration and the vibration force, and within this vibration force you have something like what? M omega squared E sine what? Omega t. So this is the vibration force. The amplitude is just the coefficient of the sine function, which is M omega squared what? E, right? Good. So So our vibration force F naught will be equal to what? Me omega squared. What the force, okay, so let's just, the equation of motion is mx dot dot plus cx dot plus kx equals what? Me omega squared sine omega t. All right, so the coefficients of this is the force, and the coefficients is the amplitude of the force. So the question is asking for the amplitude, so we can say F naught will be equal to what? Me omega squared. The me was given as 10 kilogram millimeter. See, so that should give you an idea. All right, so from here, the E is called eccentricity. Now this is in millimeters. You need to convert it to what? Meters. So we have 10 kilogram. This is multiplying, so just multiply by 10⁻³ times 10⁻³ multiplying omega squared, which is what? 157.08 squared, and that gives us 246.741. 246.741. All right, so let's see, we have 246.74 right there. The next question is to find the force transmitted. So the force transmitted over the F naught is equal to, let's see our formula sheet. Yes, F naught, Ft over F naught is equal to what? 1 plus this and that, and that is our transmissibility given up here. All right, good. So this is equal to T, and T is given at TR given as what? 0.5. So we are saying Ft will be equal to what? F naught times 0.5, and that gives us 0.5 multiplying 246.741. All right, and that gives us 123.37. All right, so that is this here, 123.37. Okay, the next is to find determine the natural frequency of the system. All right, so we need to find omega n. We know omega. What don't we know is the what? We know operative frequency. We don't know omega n, but we know tau is equal to what? Omega over omega n, where this is the frequency ratio. All right, now what can help us to get this tau? The transmissibility function given. That function is equal to square root of 1 plus 2 zeta tau all squared all over 1 minus tau squared all squared plus 2 zeta tau squared. All right, so I advise my students, you can expand this, but for objects it's a lot of time, right? So you just have to put everything in the calculator and then make it solve for you. So you're going to have something like t, which is 0.5, is equal to square root of 1 plus 2. The damping coefficient is given as well, 0.4. So you put 0.4 here times 0.4, and then the damping coefficient, the tau you don't know, you represent it by what? A variable, let's say x or y. All right, squared, and it brings, so here will be 0.5, then you go to alpha, you punch the equal to sign where the calc is, then bring the square root 1 plus, you put the numbers here, and go to alpha, you put x here, and then you have 1 minus what? Another alpha x squared all squared plus what? 0.4, and then 2 times 0.4, and then your x again. Then you go to shifts, and then you press what? Calc, not equal to straight to shift, and then the solve. And then to solve it for you, you get x to be negative 2 points. So you get x to be equal to negative 2.13915. Now, this is just one of the answers. You see here, it is power 4, right? So the solution are going to be 4. You have 4 complex and 4 real. Now, this one here, we just have plus or minus, okay? It's a square root of 4.56. Now, your calculator can only produce a negative one. All you need to do is to ignore the negative sign, all right? So x, which is tau, will be equal to 2.139. So we know omega, or the operating frequency, to be what? 157. Where is it? We know the operating frequency to be 157.08, and we know tau to be this. So since we know tau is equal to omega over omega n, we can say omega n is equal to what? Omega over tau, which is 157.08 all on 139, 2.139, and that gives us 157.08 out of 2.139, and that is 73.422 rad per second. All right, so yeah, this gives us the natural frequency. What do we have here? What do you have here? Yes, so determine the natural frequency of the system. Determine the natural frequency of the system in RPM. Now, what we have here is what? Rad per second. So to convert to RPM, we multiply by what? So 73.46 times 60 on 2 pi. So 73.46 times 60 on 2 pi. And that gives us 7. So omega n will be 701.4 RPM, right? And our answers, we have come over here 700 here. All right, so yes, we pick this. Now find the stiffness of the mounted spring. Find the stiffness of the mounted spring. Now we know that omega n is equal to root what? K on m. All right, and K is what you are looking for. The mass was given in the question as 40. All right, the mass was given as 40 kilogram. Okay, so we are going to have omega n squared times 40 is equal to K, and omega n is 73.42. Don't use the RPM, it's the rad per second. So 73.422 squared multiplied 4 equals what? K. So 73.422 squared multiplying 40, that gives us what? 215,631.60 equals K. Let's see our answers. Okay, so we have 216 kilonewton, and of course that should be it. All right, so if you run it, this is 215, right? 631. So if you run it 1, 2, 3, that would be 216 times 10 power 3 Newton per meter. Okay, so that is that, and the next are some common basic questions. So the desirable vibration is in you don't want vibration in electric motor, you don't want vibration in moving engines. So yes, we desire vibration in mobile phone because we need that vibration to alert us that we've had a call. Next, the undesirable vibration is in electric motor, of course, right? So we want this, we don't want this. So we can't say both and we can't say none. The amplitude of vibration at resonance, yes, is very large, infinity. I hope you know that. And the system governed by the equation mx dot dot plus ks equals 0. Okay, so it's positive. It's stable when k is positive. I mean, for the rest, I'm leaving it to you. If you want these questions, okay, let me know in the comment section. This can be done with the AI or the internet. So yeah, that's that for the calculations. When we come here, explain the term resonance and distinguish between operating frequency. Okay, so resonance occurs when the let's do something here. So for a force system, if you force a system to vibrate, you vibrate with an operating frequency, which is the omega. So with a force system, let's say force on damped systems, we are going to have something like the response x naught being tau, no, delta rather, delta over 1 minus tau squared. Let's check our formula sheet. So for force, this is a force system and on damped, right? So x naught is what? Delta over 1 minus tau squared. So here the tau is what? Omega over omega n. So when omega becomes equal to omega n, this becomes what? This approaches 0 and the whole thing approaches what? Infinity. All right. So when you force a system to vibrate at certain omega equals to omega n, then the amplitude is going to what? Become very great, such that the body cannot contain and there's going to be collapse. All right. Now the difference between operating frequency and then the natural frequency. The natural frequency is the frequency by the system itself, and then the operating frequency is the frequency introduced by the external force. So when the body is vibrating, free vibration based on or due to its mass and its spring element or spring value, it gives the body some amount of what? Frequency. Now, if you bring an external force to make the body vibrate, that force comes to vibrate at its own frequency, which is the operating frequency. The whirling of shafts is just as the frequency at which resonance occurs, right, in the shaft. So when a shaft is rotating, there's this frequency that when it rotates at that, the shaft is going to also what? Collapse or reach resonance, of course. Now let's quickly take this question. I mean, I was actually contemplating whether to solve this or not, but let's see. So yes, before we begin with this, if you've not subscribed to the channel, kindly do so. I'm counting on your support to be able to do this again. So there's a dumbbell problem. Let's catch here. The motion of a 50 kilogram pendulum is controlled by a spring and dashboard. The stiffness K is 10 kilonewton per meter and the dashboard piston has a mass of 0.45 kilogram. The bell crank lever of mass 3 kilogram and radius of gyration 50 mm about its center of gravity, which is at the fulcrum. When the mass is dissipated from its equilibrium position and released, the amplitude of resulting vibration is reduced by 1/2 over 3 vibrations, and are supposed to determine the coefficients of the dashboards and the value required to give critical damping. All right, so which is the critical damping coefficient. Also find the response of the system if the initial angular velocity and acceleration are pi on 50. Okay, supposed to be initial displacement and velocity, not initial whatever it is. Okay, let's sketch this. So let me use a line. So I have this, and then let's say I have my damper here and the dashboards here. All right, so let's say the distance from here to the fulcrum is x, and the distance from the dashboard to the fulcrum is y, and we have the mass here, so the distance from here to here is h. So if we rotate, if we excite the body, the system is going to look something like this. Let me just show. It's going to be something like this. All right, so at this stage you have the damper acting on it and then the spring force acting up like this. So this is y and this is what x, isn't it? So the y will be in terms of components y sine theta and y cos what? Theta, and x will also be in components x cos theta, x sine theta. All right, and then we have the weights, and that will also be in components mg sine theta and mg cos theta. Okay, so what we say is that sum of the moment about the fulcrum should be equal to what? I theta dot dot. So sum of moments about O should be equal to I theta dot dot. Now the moment I have the dash of the dashpot, now the dashpot will take the derivative of this. So I have negative d, no. So the coefficient first, c. Now we assume that the direction for the movement of the body itself is positive. The body is rotating in this direction. So every moment that goes this way will become negative. Now the damper is moving up, the spring is moving up, the weight is going this way. So they are going to be negative. So I have negative c d dt of what? Y sine theta. Don't forget y is the constant. And then minus k, sorry. So this is just the force. We want the moment. So this force, the perpendicular distance will be y cos theta. All right. And then the spring, we have minus k x sine theta, which is the extension in the spring, multiplying what? X cos theta, what is the vertical distance. And what else do we have? Mg, so plus minus, oh, why do I have plus? Minus mg h sine theta to be equal to I theta dot dot. Now the I, we're going to have I for the mass and then I for the fulcrum, which is going to be what? Mk squared for the fulcrum plus what? Ml squared for the mass. So for the fulcrum, the bell crank, they give us a mass of 3 kilogram and radius of gyration of 50 mm. And then this mass is 10 kilogram and we have 75 Hz. So yes, before we get into the values or number substitution, let's simplify our equation. Now we know for angles smaller, closer to 0, sine theta is approximately theta and cos theta is approximately 1. So in here, you're going to have minus c, need to move to the direction, minus c here, d dt of y sine theta will be just what? Y theta dots multiplying y, and then we have minus k x theta multiplying x minus mg h theta to be equal to I theta dot dot. So in the end, this one will yield, this one will give us minus cy squared theta dots minus k x plus mg h theta equals what? I theta dot dot. All right, so from here we can say that I theta dot dot plus cy squared theta dot plus into brackets kx plus kx squared plus, so here I have x here and x here, so it's supposed to be x squared plus mgh equals what? 0. So let's do our value substitution. So in the question, what else do we have? We have the mass. The mass of the pendulum is 50 kilogram. 50 kilogram, not the 10 kilogram shown. So this is the pendulum. This is the pendulum here, right? So 50 kg, not the 10 kg. And then we have spring stiffness to be 10 kilonewton. Now, before we continue, please, if you've not subscribed, kindly do so. And if you've watched the video up to this point, I believe you've really enjoyed some parts. So I need a like on this video, and that will be your support for what we do. All right, so let's continue. So from here, I have the equation of motion. All right, and then equation of motion is this. We need to find the values one by one. So the I I said is what? The I for the pendulum plus the bell crank. The bell crank mass, so the formula is mk squared plus m L squared or mh squared. So the m for the bell crank, so let me just put bell here and then the pendulum here. So the bell crank, the mass is 3 kilogram, radius of gyration is 50 mm, so 50 times 10 power negative 3 squared, plus the mass of the pendulum is 50, and then the height is 75 mm, so 75 times 10 power negative 3 squared, and this gives us 3 times 50 times. So yeah, we have 0.2887, or let's make it 2888 kilogram meter squared. The y value is 75 plus 25, and that's going to be 100. So 100 millimeter, which is 0.1 meters, right? So y is 100 mm, giving us 0.1, and then the x is 75 mm, giving us 0.07, and then h is 75, giving us 0.075. All right, so let's make our substitution. So we have 0.2888 theta dot plus c 0.1 squared theta dot plus the k. The k is giving us 10 kilonewtons. So 10 times 10 power 3 multiplying x squared 0.07 squared plus the mass 50 kg, g 9.81, and then the h 0.075 theta equals 0. So from here, let me change the pen and make it black. Okay, so from here, let's just simplify. So we have this, so 0.2888 theta dot plus 0.1 squared 0.01 c theta dot plus, so we have 10 times 10 power 3 multiplying 0.07 square plus 50 times 9.81 times 0.075. Okay, so we have 85.787 theta equals 0. So from this expression, whatever is here is m equivalent, whatever is here is our c equivalent, whatever is here is our k equivalent, and that's that. All right, so we are supposed to, so this becomes free dam system. All right, free dam system, and we were given that the amplitude 1, your amplitude after over 3 vibrations, so that is what, so you have 4 oscillations, so a4 is what, half of what, a1. All right, good. So this logarithmic decrement, determine the damping coefficient. So the damping coefficient, like from logarithmic decrement, let's go to our formula sheet. So right here we have ln a1 on ar is equal to this, and this is also known, so we want zeta, so we are going to use this formula. So zeta is equal to delta on square root of 4 pi squared r minus 1 all squared plus delta squared. All right, and from the formula, delta is equal to ln a1 over ar, in this case which will be ln a1 over a1 on 2, giving us ln 2. Now we know delta now, right? So ln 2 0.693, so zeta will be equal to 0.693 93 all over square root of 4 pi squared. R will be 4. So 4 minus 1 all squared plus 0.693 squared. And that will be 0.693 all on square root of 4 times pi multiplying 3 squared plus 0.693 squared. So we have zeta to be equal to 0.065 as a damping ratio. All right. So we know the damping ratio. The question asks us for what? The damping ratio and then the critical damping coefficient. So the critical damping coefficient, we know that for a system like this, if this is representing our mass and this is our K equivalent, then we can say that the CC for this system is going to be what? The M2 times square root of the M equivalent times what? The K equivalent. So CC will be equal to 2 roots M equivalent 0.2888 multiplying the K equivalent, which is what? 85.787. So CC will be equal to square root of 2 square root of 0.2888 times 85.787. So that gives us 9.954. All right, 9.5954. So now we know the critical damping coefficient. Okay, so we're supposed to determine the damping coefficients of the dashpot and the value required to give critical damping. Okay, so we solve for the damping ratio. All right, and we solve for the critical damping coefficient. But the question asks us to find the C value here. So to get a C value, we know that C equivalent over the CC will be equal to the damping ratio. So C equivalent will be equal to 0.065 times the critical damping coefficient, which is what? 9.954. And that will be 0.065 times 9.954. So we have 0.646 here. Now we know that C equivalent is equal to what? CY squared. No, let's just take it straight from our equation of motion. The C equivalent is what? 0.01 C. All right, so 0.01 C. So 0.01 C will be equal to 0.646. So C will be equal to 0.646 out of 0.01. So C will be equal to 64.6 kilogram per second. We have been able to find the damping coefficient of the dashpot, and we've also found the critical damping coefficient. The next is to find the response of the system. All right, so the response of the system, this is free damp system. All right, so the response X at any time T will be equal to what? And it's under damp, right? So A exponent minus zeta omega nt sine omega nt plus phi. All right, so you need to find phi, you need to find A. Now the formula sheet, if you come to our system, we can find phi, we can find A and make the substitution, and you are done. So I'll leave that for you to try. So yes, this is the end of the trial questions for your revision. If you enjoyed the video, kindly let me know in the comment section. And once again, if you have not subscribed, kindly do so. At least you can like this video as a form of appreciation. Thank you and all the best in your exams. Good luck.